Great, thanks very much. So yesterday I kind of gave a talk that was more of an overview of lots of different work that's going on in NLP and some of my opinions about how NLP and machine learning are related. And as part of that, I sort of started to talk about this theme of developing better tools that can learn reasonable representations and do good things with less available data. But I didn't really hone in on that very much. So today what I'm going to do is I'm going to try to focus more in detail. Rather than looking at a kind of range of different papers from other people across the field, this is going to be much more of a talk about my own research in trying to develop technologies that do actually learn effectively from less data. So, as I mentioned yesterday, there's been a lot of recent success in the field of speech and language technology, and I mentioned a bunch of different application areas. And yesterday what I pointed out is that a lot of the successes in recent years have come from the deep learning revolution. But implicitly in that, what I didn't mention so much is the fact that another aspect of what's helped develop these technologies is the use of supervised machine learning, much more generally. Right? So the idea with supervised technology, as I'm sure you all know, is that you've got some training data that has a bunch of labels on it. Right? You take your labeled training data, you plug that into your machine learning algorithm, whether it's a deep learning algorithm or something else, and out the other end comes some kind of prediction function that ideally you should be able to use to generalize beyond the data that you've seen and make predictions on unlabeled test data or deployment or whatever. Okay. So as I said, that works really well for lots of things. But of course, it does have problems. And one of the big problems is that getting that labeled data in the first place is not always easy to do. And in particular, if we're looking at language technology, we often have to pay people to create these labels. So we're looking at, say, a speech technology system. We need to have transcribed speech, which means that someone actually needs to sit down and listen to all of this audio and write out the words that are in it. And that's obviously something that takes a reasonable amount of money to pay people to do, but it can be even worse than that. So if we're developing some other kind of NLP system that maybe we need annotations for tree structures, right? So yesterday I talked about kind of tree structures that have labeled latent nodes in them, but this is a different kind of tree structure that's called a dependency tree. But again, to kind of make these labels, an annotator needs to have a lot of specialized linguistic knowledge and training, right? So it's worse than just paying a random person off the street. You've got to do more than that. And so the result of that is for many languages, these kinds of resources, labeled resources, are unavailable. And one of the things I talked about yesterday that could help to alleviate that is that perhaps we could try to do leverage unlabeled data. But it turns out that even unlabeled data is not always easy to get for certain languages, in fact, for many languages. So linguists estimate that there are probably about 7,000 different languages spoken in the world, and it turns out English is very, very popular, as I'm sure you all know. If you look in Wikipedia, English has about 5.8 million Wikipedia articles written in English. And that's, of course, a great source of unlabeled data to train gigantic billion-word language models in English. But if you look at other languages, only about 141 of them out of 7,000 have more than 10,000 Wikipedia articles. And even 10,000 is a lot less than 5.8 million. Right? So that's a problem right there. And even worse, many languages in the world actually lack a written form entirely, so you're not going to find anything in Wikipedia. Or they may lack a sort of standardized written form. And some languages that lack standardized written forms actually are very widely spoken languages. So in fact, Arabic is one of these languages. There is a standard written form of Arabic. It's called Modern Standard Arabic. And that's used very widely across many Arabic-speaking countries. But all of the countries also have their own particular dialect that people speak in everyday language. And those dialects actually vary from one another by quite a lot. And until very recently, no one actually ever wrote them down, although recently people have started writing them in social media because, as I mentioned yesterday, it's much closer to the way people actually talk. But because there was never a standard form, the things that people write in social media vary a lot, right? So there is no standard form for that language, or I should say for those languages, varieties of Arabic. Okay, so the result of all of this is that there's really a lot of unequal access to language technology. So if you look as an example at Google Translate, at the moment, and this is interesting actually because I originally wrote this slide about 2 years ago and it hasn't changed since then. Google Translate includes about 103 languages, but if you look at what those languages are, nearly half of them are European languages. There are a number of Asian and African languages, none from other parts of the world. But even if you start to kind of home in on what's going on there, what you'll notice is that only 9 of India's 22 official languages are included in Google Translate. And there's at least 5 African languages with over 10 million speakers that are also missing from Google Translate. Right? So it's not just missing, very tiny languages. But there are also a lot of very small languages, endangered languages of North America, for example, that are not included. And as I said, there's really about 7,000 different languages in the world. Many of them are minority languages. They're endangered languages. And I think that by not including these in our modern technology systems, it kind of discourages people from using those languages. And it also sends a message. It kind of says, your language is not really important to the modern economy and the technological progress of the world. And I think that's not a great message to send. Partly, just kind of from an ethical perspective, we would like to be more inclusive. But I think even from a kind of scientific perspective, there's lots of linguists and cognitive scientists who really have, and anthropologists who have a lot of motivation to kind of keep these languages alive as a way of understanding and studying the diversity of human language across the world. So there's lots of reasons why we might want to encourage people to keep speaking minority and endangered languages. And I think that by developing this kind of technology, that can be one way of helping with that. So if we're thinking about trying to develop technology for these kind of lower resource languages, there's really 2 possible directions to take. One of them is a minimally supervised kind of scenario where we might have a small amount of labeled data as well as perhaps some unlabeled data. And the other one, which is the one that I'll focus primarily on in this talk and in my research, is to take a kind of fully unsupervised, or maybe we could think of it as a distantly supervised approach. So we'll assume that we don't have any labels at all for the task of interest, but we might have, in some cases, other information or other labels. Those might include translations into a different language, maybe some images, other kinds of context. And I think what I've learned from sort of looking at different work that people are doing in this space and my own work is that we really need a variety of different approaches because all of these endangered or low resource languages kind of have their own particular issues and different kinds of data might be available for them. So I think it is important to look at a number of different ways of dealing with this. And I'll talk about, as a result of that, both unsupervised monolingual models, that's going to be sort of the first part of my talk, as well as how to use information from other languages. But before I get to those, I want to just give you a little bit of background to sort of get everyone up to speed on speech technology. Well, I'm not going to say everything about speech technology, but to try and give you a little bit of a sense of what's hard about dealing with speech in particular from a machine learning perspective. So the first thing that you might be asking yourself is, I'm going to be talking about unsupervised automatic speech recognition. What does that even mean? Right? It's not so clear what it means to do unsupervised speech recognition because if we don't have labels, right, the labels are the words. Right? So normally speech recognition kind of by definition means that you're taking speech and turning it into the words, right, which are the labels. So if you don't have any labels in your training data, what are you going to do? Okay, so what a lot of people have done for the first kind of few years that people were working on this problem is something called unsupervised term discovery. And the idea of unsupervised term discovery is you basically have a large corpus, an audio corpus, and what you're trying to do is not necessarily identify every single word in there, but you're trying to sort of find little matching bits of speech. Right? So we might find, okay, here's a little bit of speech that sounds like this bit of speech and sounds like that bit of speech. And so if they sound similar enough, then maybe let's extract them and cluster them together, and we'll assume that that's a single term. So it's just different instances of the same word that occurred in that corpus. Right? And so the idea of this method is to have a sort of high precision, we'll pull out things that we're pretty sure are correct with low recall, right? So there's a lot of the corpus that we're just not going to deal with at all. And typically these methods are kind of based on heuristics. They can still be useful, right? And one of the things that we could maybe use this for is a query by example system. So you could imagine if you have a very large audio corpus, for example, well, I'll talk about an example that's kind of like this a little bit later in the talk. You might have a large set of recordings from radio, let's say, and you want to be able to bring back recordings that have a particular keyword in them, right? So you could just speak the keyword that you're interested in and go and try and bring back documents that match that. Right? So you never actually had to transcribe anything. You just say, oh, it should sound like this. Bring me back documents that sound, have words that sound like that. And you can imagine extending that to things like document clustering and navigation and stuff like that. What I'll be talking about, at least in the first part of this talk, is actually a slightly different approach, where we're trying to be a little bit more ambitious. And rather than kind of ignoring lots of the data as background, we actually wanted to come up with what was as close as possible to a real supervised system as we could think of, which is basically a full coverage system, right? So we're going to deal with all of the data, and we want to essentially segment that, so figure out where the boundaries are between the words in it, and also then, once we've identified those, hopefully cluster together the different instances of the same word. Okay. So the idea here is that we're going to have a much higher recall system, potentially with lower precision. But the fact that we're covering the entire data has the nice benefit that we can actually use a probabilistic model to do this. And I'll explain that in the talk a little bit later. Before I get to that, though, I want to go through a sort of little bit of background by explaining what you might kind of imagine as the way of dealing with this. This is actually not how we do it, so this is kind of a straw man, but it should give you an idea of what's hard about this problem. So if we think about how a traditional supervised ASR system works, so this is pre-deep learning, this is a probabilistic model, it's a generative model of speech. The way that it works is it kind of assumes that the way the speech is generated is we start with the words, right? So there's some sequence of words. Those are then converted into a sequence of phones or speech units. And this, there's typically some resource that we have, like what's called a pronunciation dictionary, that can convert those two things. Once we have this sequence of phones, we generate the actual speech by assuming that each of those phones generates a number of states, usually 3 states, in an HMM type of model. And then each of those states generates some number of what are called frames. So frames of speech are basically just vectors that model some very small, or represent some very small amount of that speech, so 10 milliseconds, let's say. Right? So it's just a vector that represents the acoustic signal, and each of the states in the HMM is responsible for generating some small number of those. Okay, so that's our generative model. So if we were going to do unsupervised learning on this, what that means is that we would sort of come in at the bottom, we'd have the features available, and we'd need to do inference. Right? So you could imagine that working something like this. Right? Obviously, the first thing is we need to extract the features from the speech, and we can do that using just kind of standard signal processing-based methods. So the kind of traditional features that people often use are called MEL frequency capture coefficients, or MFCCs. Right? So we would extract those from the speech, and then we just apply some kind of clustering to cluster those features together and get a sequence of cluster labels. And then there are methods that have been developed by myself and others that you can take this sequence of cluster labels and you can kind of group them together somehow in order to find the words. Right? So we could imagine doing that. It turns out it doesn't work. I've tried. And one of the reasons that this doesn't really work very well is that this is effectively a pure bottom-up approach. And bottom-up just doesn't work very well for speech. Speech just has a huge amount of variability in it that prevents this from working well. And that variability comes from a lot of different places. So it comes from the speaker, right? So if I'm talking, it's going to sound very different from if someone else, especially if they're a male. Sorry, that's the gender thing, right? But even some other female speaker is going to sound quite different from me. We also could have channel noise, right? So if I'm, my recording happens to be on a telephone versus a close talking microphone or something like that, it's going to sound very different. And even the phonetic context actually varies, changes the sounds a lot, right? So I had two example words, speech and feels, right? Both of those have an E sound in them, but it turns out that the acoustic properties of that E sound are actually very different in the context of the word speech and the context of the word feels, just because of the surrounding phones in those words and the articulations that I need to make. Okay, so there's a lot of variability that we need to overcome. And interestingly, there's actually some evidence from cognitive science that even human infants are probably not doing pure bottom-up learning when they're sort of doing their very early learning of speech. So if we look at evidence from developmental psychology and when infants are learning different things, what we'll see is that starting around the age of 4 months, we have some evidence that infants are beginning to learn something about vowels in their language and then consonants a little bit later. But even at the very same time, actually, there's some experiments showing that infants are able to recognize their own name at around the same time. And, again, very early on, words in sentences. Right. So that suggests that these processes are not really independent of each other. It's not like we learn about the sound categories and then we start building words, but actually perhaps there's a joint learning process going on. So what we'd like to do here is try and kind of use that kind of insight to try and develop better models. So first I'll talk about this idea of unsupervised monolingual models, and I've got two different models that I'll talk about. One of them is using top-down information to try to improve subword representations, and I'll say a little bit more about what that means. And then I'll talk about a model that uses that information but also goes on to do the full segmentation and clustering task. So the first model here is something that we're trying to improve the speech features themselves. So remember what I said is the first step that we need to do here is actually take the speech signal and extract some kind of features from it. And I'm going to, in the next few slides, actually show this speech segment slightly differently. So this is basically showing the spectrogram. So we still have time here on this axis and the frequency of the signal on this axis, and the color just represents the energy. But actually, all of that doesn't really matter. All you need to know is that what we're going to do is sort of extract, a single, again, a single frame of this and what we do with it. Okay. So as I said, traditionally we use signal processing methods to extract these vectors and plug them into our whatever it is, speech recognition system or machine learning method. And what we'd like to ask here is, can we use machine learning to actually improve this and learn a better representation that can abstract away from unimportant variation but capture variation that is actually critical to the phonetic content that we care about. So if we're thinking about doing unsupervised representation learning, one of the maybe obvious things that comes to mind is to use something like an autoencoder. And an autoencoder is, I think Ian actually mentioned this yesterday, it's basically a neural network that takes an input vector, maps that through a number of hidden layers, and then what it's trying to produce as the output vector is actually identical, should be identical to the input vector. Now, something you might notice here is that my hidden layers are actually larger than my input and output, which means that in principle, this autoencoder could actually just learn to perfectly, it doesn't actually have to abstract anything here, right? It can just encode the input vector exactly and reproduce it. And that's not very interesting. We want it to actually abstract in some way. And so one thing that people do to try and encourage that is they will use a denoising autoencoder, right? So instead of just using the input vector itself, you'll sort of add some random noise to that, and as a result of that, the model does need to actually try to, figure out what's the noise and what's the signal here, and encode the signal in order to reproduce it as well as possible. So we're going to kind of jump off from that a little bit, right? So a denoising autoencoder, this random noise. You can think of what we're doing as actually, instead of having random noise, trying to introduce some noise that's actually sort of natural variation in the signal. So we call this a correspondence autoencoder. And the idea here is that now we're actually going to use two examples of a word to train this model. And what we'll do is we'll actually first align the frames in those words, right? So remember, if we're looking at two different examples of a word, right? If I say some word twice, in one case, I might say it very quickly, and in another case, I might say it very slowly. So they're not necessarily the same duration. So what I need to do first is align the frames to basically say, okay, here's the bit of this word that sort of corresponds to where it is in the other word, in the other token of that word, the other instance. And once I've done that, and there are sort of standard ways you can do that called, the method we used is dynamic time warping. Once you've done that, you can then extract pairs of frames that are pretty much corresponding to similar parts of that word. So it might be, this corresponds to the beginning of the vowel here and the beginning of the same vowel in the other instance. And that's what we're then going to use to train our autoencoder, right? So basically we want to train it to kind of be able to extract whatever it is that's, similar and, important about representing those two different instances while abstracting away from whatever is different between those two instances. Okay, so that's really nice. It sort of has this idea of an autoencoder, but generalizes it a little bit. But you might be wondering, I was claiming that this is a fully unsupervised method, but I'm also claiming that I'm using examples of, where the two examples are the same word. So how does that work? And the answer is, well, we actually just used the method that I mentioned earlier, an unsupervised term detection system, to get those pairs. Okay, so what that means is that those pairs are actually very noisy, right? Because this unsupervised method is not 100% accurate at identifying pairs. Nevertheless, what we found is it actually works reasonably well. And in fact, in some later on, I'll talk about what happens if we use gold standard word pairs as well. But for now, let's just assume we use unsupervised pairs of words to train this thing. And so now we need to evaluate and see whether our learning is actually working. So the way that we want to evaluate this is by basically figuring out, okay, if we replace our MFCCs with this new learned feature representation, does that actually help us? And the way that we figure out if it helps us is, does it actually allow us to better discriminate between words that are different and identify that two words are the same when they really are the same? And we're going to do this in a slightly more fine-grained way, actually not just looking at full words, but looking at what are called triphones, so basically just 3 phones in a row. So we use this thing called an ABX task. Right? So you imagine that there's one speaker who has at some point produced, let's say, the word bug and the word bag. So those two things vary by just a single phone in the middle. And then we present a different speaker's instance of one of those things, in this case bug, and we ask the system to tell us, is this more similar to speaker 1's bug or speaker 1's bag, right? So can it actually tell what's the same and what's different when it needs to? And so if you look at the results that we got, right, so we compared the MFCCs, which is the, kind of traditional features, with a regular autoencoder. These are error rates, right? So lower numbers actually means better, right? So you can see that actually the autoencoder is helping in some cases. I should say that obviously we're testing on 2 different languages here. English and Tsonga, which actually this is very appropriate for this audience because Tsonga is actually a language that's spoken in South Africa as well as surrounding regions. I think it has about 12 million native speakers. So those of you who are not from South Africa may never have heard of this language, but it's actually a pretty widely spoken language. Nevertheless, it is a low-resource language. Okay, so our autoencoder makes things a little bit better. The denoising autoencoder also makes things a little bit better, but this correspondence autoencoder, as you can see, definitely improves the results further. And importantly, what we found was that the correspondence autoencoder particularly improved results across speakers, which is what we were hoping for, right? Because we're hoping to kind of abstract away from the differences between speakers. So that's really nice. What it tells us is that even very noisy top-down information from unsupervised term detection can help us to learn better subword features. But so far, these results are just on this intrinsic discriminability measure. So what we'd like to know is whether these features can also improve word segmentation and clustering. So that's what I'll talk about next. Again, just as a reminder, the approach that we could be taking, but we're not going to, is sort of extracting speech features, trying to cluster those, and then grouping them into words. And I sort of said, oh, this doesn't work, I've tried it. And it's actually not just me that's tried it. So there's various ways that you can try to develop a model that's kind of like this, that does, in fact, have a somewhat similar probabilistic structure to the generative model I talked about, where it's modeling individual phones, and you try to incorporate something that accounts for this variability. So there was a few different models that were proposed that do things like add a noisy channel model or relax certain kinds of independence assumptions. But they still end up having very complex inference methods and hadn't actually, people had tried them on single speaker audio, but had never been demonstrated on multi-speaker audio, which is what we were really interested in doing. So we kind of want to think about scaling these things up. So we're going to take a slightly different approach here to try and simplify the inference and various other things. And we're going to model entire words holistically. So we're actually going to take the phones, not try to think about words as sequences of phones, because then we get into these issues of assumptions about independence between the sounds in the phones, which actually isn't true. And I'll say in just a second how we do that. But we can still use probabilistic models, and in fact, doing this, modeling these entire words holistically, will actually make the probabilistic model a lot simpler. So the main results that I'll talk about with this model are that we're able to achieve good multi-speaker clusters on a small vocabulary. We're able to also run this on a large vocabulary data set and outperform some competing systems that were developed for single speaker, and as far as I know, this is also the first system that was actually tested on large vocabulary multi-speaker data. So the kind of basic underlying idea that we used here to model the words themselves is something that's actually, I think, much more widely known now, which is acoustic embeddings. So the idea here is we basically just want to represent variable length segments of speech in a fixed dimensional space. And hopefully, if we can have good embeddings, then the idea is that all of the different instances of this particular word are going to be in one part of the space, and all the different instances of this word will be in a different part of the space. And so then if we do clustering, it should work. So that's the hope. So how do we actually get these acoustic embeddings? Unfortunately, I don't have a fancy machine learning method to tell you about here. I have something really dumb, right? So this is a kind of good lesson that sometimes the really dumb baseline is actually good for various reasons. First of all, it's fast, and second of all, it turns out it actually works better than a lot of the other things we tried. So we're just going to do downsampling. Okay, so what that means is we take our different instances of words, which initially, when we extract features from them, that might mean that this one is longer, so it has more features that we extract. But then what we're going to do is we're just going to take every n of these frames, where n is bigger in this case than this case, so that we end up with exactly the same number of frames in both cases. Okay, so it's not very exciting, but it works. Well, works-ish. Okay, so we've got these embeddings. And then we need to actually think about how do we model what's going on in this embedding space. So we can think of this as an acoustic model, right? The data points in our space are these embeddings. And we're just going to use a Gaussian mixture model to capture that, right? So we're going to assume that each of the lexical items that we care about is a multivariate Gaussian. So it's got its own mean and standard deviation, covariance. And so given some particular lexical item k, we can model the probability of the data point, some instance of that lexical item, as I said, a Gaussian distribution. And so to figure out which lexical item x should belong to, we just say, okay, well, the probability that it belongs to cluster k, given the means and covariances, is that likelihood there times the prior over the clusters, right? The prior probability of that particular cluster. So that's really nice. As I said, this is a pretty standard kind of model. And so what that means is that if we know the word boundaries, which of course we don't, but I'll get back to that in a minute. If we know the word boundaries, and if we know the parameters of the acoustic model, which again, we don't, but I'll get back to that, right? Then things are very simple, right? We could just assign each of the embeddings to some particular lexical item, right? Some component of that GMM according to the equations that I just mentioned, right? So we just take our segments, map them to their embeddings, and then figure out which cluster each of those embeddings belongs to. Okay, so let's back off of some of those assumptions, right? So suppose we only know the word boundaries. Okay, well then we just have an unsupervised clustering problem, right? So in order to solve that, we're going to take a Bayesian approach. We're going to add priors over our we're going to add priors to the model. We're going to integrate over the cluster weights and the means, right? And we can do that using a Gibbs sampler, right? So we'll just use that to cluster the embeddings while simultaneously learning the acoustic model, right? So we initialize the clusters at random, and then we're going to kind of iterate through and resample a cluster for a single embedding at a time, conditioned on all the other clusters. Okay, so this is a fairly standard approach. So that's good, right? So that's for the word boundaries. But again, we don't know the word boundaries. So let's kind of go from the other direction. Let's imagine that we know the acoustic model, right? So we know this Gaussian mixture model. We know all its parameters. If we know that, we can actually use that information to compute the best segmentation of each utterance, right? And so the way that we can do that is we say, okay, well, let's just imagine this particular segmentation here. If we have this segmentation, then we take each segment, we figure out its embedding, and we have the acoustic model so we can figure out what the probability of all these embeddings are under that acoustic model. But of course, if we can do that for one segmentation, we can just as well do that for a bunch of other segmentations. And so we can compute the probabilities of each of these different segmentations under the current acoustic model, and we can just choose the segmentation that's best. Okay, so I've said, you know, if we have the segments, we can use those to do clustering, and if we have the acoustic model, then we can use those to figure out the segmentation. So those of you who have experience in machine learning can probably guess where I'm going from here. We're going to use a Gibbs sampler to actually alternate back and forth these two components, right? So we're going to initialize everything at random, choose a random segmentation, and just assign segments to clusters randomly, which gives us an initial acoustic model. And then we're going to iterate a lot, right? And we're going to say, okay, every time we iterate through the whole data set, we'll choose each segmented utterance. We'll remove the embeddings of that segment from our acoustic model, resample its segmentation, and then add the new embeddings back into the acoustic model. So this is actually sort of jointly learning the segmentation and the acoustic model. And you can imagine that, you know, this is computationally fairly expensive. It was not easy to implement, and so initially we were like, okay, let's just try this on a really small test case to figure out if this works at all. So the first thing we tried was a small vocabulary data set. And so in the small vocabulary data set, this is the TI digits corpus, and it's a corpus of English digit sequences, so it just has 11 words. But it does have a lot of different speakers. So let me just play you, hopefully this will work, if I play you an example of the kind of utterances that are in here. Oh, maybe I need to turn off my laser pointer. How do I do that?
1473533.
Okay, so that's just one utterance in this corpus. So it's not very interesting, right? But that's one speaker. There's lots of speakers. So we can try running the model on this. And rather than showing you numbers, I'm going to show you sort of qualitatively what comes out the other end. So this is a confusion matrix showing the results that we get from the model. Right, so there are ground truth digits 1 through 9 plus 0 and 0. And then this is a particular version of the model that had a slightly larger number of clusters. But you can see in general, it's finding pretty much one cluster for each of these. There's a few cases where it finds 2 clusters for a single digit. and I can show you, or I can play you what that sounds like. So before I do that, let me play you an example of a cluster that actually was a good cluster. So this is just a snippet of stuff that went into the 0 cluster.
0, 0,
0,
0,
0,
0, 0,
0,
0.
Okay, so that's 0, in case you couldn't tell. And then we can see actually what's going on with the 9 cluster and the 5 cluster, which are the ones that it kind of split up into 2. So here's the first 9 cluster.
9, 9, 9, 1, 9,
9,
1, 9,
9,
9,
9, 9.
Okay, so you can hear, I mean, there were a few things in there that weren't actually 9s. But what you might have noticed is that it's actually kind of getting like the first part of the word 9. And if I play this one, you will notice.
9, 9,
9,
9, 9,
7, 9, 9,
9, 9, 9, 9.
Right, it's kind of getting the second part of that word. So it's not that these clusters are bad in the sense that they're heterogeneous. The problem is that it's kind of messed up the segmentation a little bit. And actually, that's exactly the same thing that happened with the word 5. So it does seem like it's maybe over-segmenting a little bit, but in general, that the clusters themselves are actually fairly good. And so we thought, okay, well, this is good enough results that we're prepared to try and actually do this on a larger vocabulary. So we went ahead and tried to scale this up to a larger vocabulary. And in order to do that, we actually did need to make some modifications to try and get this thing to scale. So the first thing is, in the step where we're trying to consider all the possible segmentations of an utterance, there's a lot of possible segmentations. So actually, we don't really want to consider all of them. So what we did is we kind of used this bottom-up method that identifies syllable boundaries initially as a way of sort of narrowing down what possible word boundaries might be. Okay, so to the extent that this thing isn't accurate, we're not going to be able to fix that. But we should be able to potentially find, okay, well, here's where it told me there was one syllable and then another syllable, and our system could come along and say, okay, actually both of those syllables belong to a single word rather than having them split up. We also imposed a minimum word duration. That was partly because partly for computational reasons, but also partly that we discovered that it tended to over-segment things. And the other thing we wanted to do here was actually to compare the traditional MFCC features used as input to this system with our Correspondence autoencoder features that I talked about in the first part of the talk. The data sets that we used here are actually the same ones that we used in the previous part. So we tuned the system on part of our English data set, and then we tested it on a different part of the English data set, but then we also tested it on the Tsonga data set without any retuning. It's also important to point out here that these two data sets are, have fairly different characteristics. So they're roughly similar in the number of hours of data. They're both pretty small, well, very small. The Tsonga data has a few more speakers, but what you'll notice is that actually it's also harder because the number of tokens per type, in other words, the number of different instances of each lexical item is considerably lower in this data set, which means we had there's less repetition, basically. So there's more different speakers and less repetition, which means that overall it's going to be a lot harder to deal with. And I need to tell you a little bit about how we evaluate the system as well. So we're going to use word error rate, but we have to modify this a little bit because we don't have supervised, it's not a supervised system. So the first thing we need to do in order to compute word error rate is we're going to take our clusters that are identified by our system. So here's two different clusters that it might have found. And we can look at what all of the gold standard labels are for the things that it found in those clusters. So maybe this is a cluster that's mostly consisting of gold standard 1, and this is mostly gold standard 2. And we're going to map each of those to a single label, right? So we're going to say, all right, this is mostly 1s, so we'll call this 1. And every time we saw a prediction from that cluster, cluster 1, we're going to relabel it as the word 1. And every time we see a prediction from cluster 2, we're going to relabel it as the word 2. And that will allow us then to determine whether, when we predicted the word 1, did it actually match the gold standard label 1. And that allows us to compute this thing called word error rate, which is used in standard speech recognition systems. And so the word error rate is computed by basically figuring out how many, if you align the two sequences, your predicted word sequence and your true word sequence, how many insertions are there between the two, how many deletions, and how many substitutions. And I should really point out, this is important, because actually we do get some scores that are above 100% error, right? It can be above 100% error because if your prediction adds in a lot of extra words that aren't in the true sequence, then it basically ends up, you have more errors than there are words in the true sequence. So the normalization is a little bit funny. Okay, so that's one thing to notice. And then the other thing to notice is that in this way of mapping, this is a one-to-one mapping that I'm describing here, which is actually pretty strict, right? It means that if we found some third cluster, let's say, where also the majority of the things in this cluster are the word 1, if I'm using a one-to-one mapping, I'm not allowed to map that onto the word 1 anymore because I already used it. Oh, sorry, I just realized you can't see my laser pointer anymore because it's, yeah. Okay, so if I have this cluster over here, I can't map this onto the label 1 because I already used it. So what I could do is I could map it, in this case, I've got 2 instances of Anne. I could map it to that if I haven't already used that as another cluster label. And if I have, then I might have to just kind of map this onto nothing, which means I lose all the score for that. Okay, so we computed this kind of one-to-one mapping word error rate, and then we also computed a many-to-one word error rate where we are allowed to map this also onto the 1 cluster, which obviously can give us better scores. It's a little bit more lenient. So to kind of walk you through the results here, we've got speaker-dependent results first. So speaker-dependent results mean that we are running the system separately on each speaker's data, right? So we don't have as much data to learn from, but it's more homogeneous. And then we're just going to average together all the scores that we get from those individual speakers. Whoops. So the first thing to notice is that, remember I said we started off by just having this bottom-up cluster syllable boundary detector, but our method is allowed to decide to resegment those and sort of smush 2 syllables together into a word. And doing that clearly is helping, right? So again, these are error rates, so lower is better. So if we're allowed to cluster and segment, we do significantly better than just finding the syllables. And then adding that minimum word duration also helps a lot more. All right, so we're now actually below 100% word error rate, which is awesome. And also, if we do our many-to-one mapping for the word error rate, then those word error rates, again, come down further. So that's our speaker-dependent results. Our speaker-independent results basically follow the same pattern. So this now means that we mush together all of the data into a single data set, so we have more data, but it's more heterogeneous because it includes all of the speakers. And as I said, the pattern is very similar. Error rates are a bit higher because it's a more challenging task. Okay. So, and the last thing is, of course, that we tried incorporating the correspondence autoencoder features rather than the traditional features, and did find that for the speaker-independent case, right, where we want to be able to abstract over different speakers, it does actually help in that case. So what we were able to show here was this nice probabilistic model that incorporates this idea of acoustic embeddings and combines both top-down and bottom-up information for joint segmentation and clustering in this fully unsupervised setting. We were able to show that, yeah, we can actually run this on large vocabulary multi-speaker data. I'm not going to claim that those results are super amazing, but the fact that we were able to develop this system at all and get anything, reasonable out the other end, I think is really nice, because it's the kind of first demonstration that that kind of learning is even possible. And we did outperform previous systems on single speaker data, although I haven't actually shown the specific results for that here. However, as I said, those results are kind of exciting in the, we've got this new machine learning model and, we can show that something is working. But, it might be nice if we could improve them somehow. And coming from yesterday's talk, I sort of gave a little preview of the fact that perhaps one way we could start to improve things is by not just looking at monolingual data, but actually by incorporating information from other languages as well. So in this part of the talk, I'll go through two ways that we're starting to look at multilingual data. So the first one is multilingual training to try and improve those subword representations, the feature representations even more. And then I'll get to a speech-to-text translation system. So this part is, I think, a little bit more applied, and I'll actually also talk a little bit about some work that's kind of followed on from my own that's not actually my own work. Okay, so just to kind of remind you where we were with thinking about feature representations, right? So feature extraction from speech is a hard problem because we're trying to get phonetic information out. We want to abstract away from things like the speaker and the gender and the channel noise and the phonetic context. And in the first part of the talk, I showed that unsupervised top-down information from the same language can help. And now we're going to ask, what about using supervision from other languages? So we're going to look into crosslingual supervision. We hope that this is going to help with not all of the variability, but at least some kinds of variability, right? So there's obviously differences between different languages in terms of how phonetic context might affect the pronunciation of a particular phone, right? That sort of has to do with, the accent of the language, and even the particular phones are different between different languages. On the other hand, we might expect that the kind of variability that you get due to speaker and gender and noise in the channel probably don't differ that much between languages. And so if we can learn from some other languages how to abstract away from those things, maybe that will help a lot in the language that we're looking at, our target language. And we have an even more specific hypothesis here, which is that for equivalent total amount of data, right, number of hours of speech, basically, we're going to hypothesize that using data from multiple languages will actually work better than just using data from one language. And the hypothesis arises from the fact that if we're just looking at a single other language, then we might actually end up accidentally learning stuff that's specific to that language that doesn't transfer well. Whereas if we train on multiple different other languages, then hopefully we should kind of learn what's general to all of those languages that will transfer well to the target language. So the way that we're going to approach this is using, again, a deep neural network and extracting what are called multilingual bottleneck features from this network. So the way that this network works is that it's trained to predict phone labels using data from high-resource languages. So in this case, I'm just showing three, German, Korean, and French. And so the idea is we have this network where at the input, we give it MFCCs plus I-vectors. I haven't talked about I-vectors. These is basically a speaker adaptation method. But basically, we can extract these from our high-resource language. We run that through a bunch of hidden layers that are pretty wide. And then we have this bottleneck layer that is, the reason it's 39-dimensional, well, we want it to be smaller dimensional because we're going to have to plug it into some downstream system, and having something that's too high dimensional makes that computationally difficult. But also, the MFCCs themselves that we're using as a comparison have 39 dimensions. So we kind of want to have a fair comparison here. So we kind of run this through a bottleneck layer, and all of this stuff is shared between all the languages. But then some of the input data that we're going to get will be in German, and some of it will be in Korean, and some of it will be in French. And if we're presenting a German input sequence, then we're going to compute our objective and backpropagate using the whether or not we got the German labels, the phone labels correct. And if it's Korean, then we're going to do that from the Korean one and so forth. Okay. So the point is that we're learning this single representation that hopefully captures whatever it is that we need to do phone recognition in all of these different languages. And then what we can do is when we get to our target language, and we want to extract a representation for that, right? We basically input that target language in at this point and, you know, compute everything through here and just extract whatever this learned representation is for that target language and use those 39 dimensions as our new representation for the target language input. And then we can use those to, you know, do whatever we want, whether it's plug it into a segmentation and clustering system or compute word discrimination or whatever. Okay, so the experimental setup here is our training is going to consist of about 20 hours each of 10 different languages, and either 15 or 80 hours of a single language, which in this case is English. Because remember, I wanted to sort of test this hypothesis about, you know, whether having a single language versus multiple different languages in the same amount of data actually makes a difference. And then to evaluate, we're going to do a word discrimination task. So this isn't exactly the ABX task I talked about earlier, but it's a similar concept where we want to be able to tell, given different instances of speech, are they the same word or are they different words? So we're going to do this word discrimination task on 6 different unseen languages that are not in our training data. And we're going to also plug our BNFs into an the unsupervised segmentation and clustering system that I talked about earlier. So I'll walk through both of those evaluations. Okay, so first of all, the word discrimination results. So this is just one language because there's a lot to kind of absorb here. So this is running our system after training it on 10 languages, not including Spanish, and we're going to then test it on Spanish. So there's a few things showing on here. So first of all, we're talking about a precision measure on this discrimination task, so higher is better. There's a couple of baselines on here. So there's our correspondence autoencoder features where we trained them on unsupervised word pairs. There's our correspondence autoencoder features where we trained them on gold standard word pairs, which you can see is better. But what you can also see is that actually with only just 2 languages added, so actually this isn't, it's showing in terms of hours of data, but basically each of these points on here indicates an additional language that we've added. With just 2 languages, we're actually already doing better than this. Now the difference between these two, this orange one and this green one, basically is what order did we add languages in, right? So we started off with one particular language that we trained on, and then we added a second one and a third one and a fourth one. And what this is showing is that basically it doesn't really matter what order you add the languages in. What does matter, you use different languages, right? Because here's the comparison to just using English data, right? So here's 80 hours of English data versus about the same amount of, I guess that's 1, 2, 3 languages. And you can see that having multiple different languages is actually doing a lot better than just having more English data. Okay, so that's the sort of walkthrough of that. As I said, we ran this on 6 test languages. I'm not going to walk through all of these, but basically they all look the same, right? So qualitatively, they're all similar, although the absolute performance is a bit different in the different languages. So that's really nice, because again, we've got this like intrinsic measure that tells us that these features are actually working better. The next question we might ask is, do they actually work on downstream tasks? So the downstream task that we worked on first was this, well, actually the only one that I've worked on, I'll talk about some that other people have done in a moment, is this unsupervised segmentation and clustering task, the same one that I talked about earlier in the talk. Right? So what you can see here is the comparison on, again, on word error rate. So just as a reminder, lower is better now. We're comparing MFCCs, which are our traditional features. The next bar over is the correspondence autoencoder features, which you can see actually don't help that much on English, but they do help on Sitsonga. And then our bottleneck features, which, it's not a huge improvement, but they do help in both English and Sitsonga. And again, we have these bars overall are the one-to-one mappings, and the black lines are the many-to-one mappings, which again are overall lower word error rates, but similar pattern. And we also computed boundary accuracy, right? How accurate is the segmentation, and cluster purity, and both of those things also improved. Right? So this is really nice. right? It tells us that the BNFs are definitely helping. One question that we might ask, right, I've shown that correspondence autoencoder features, which use target language data, can help, and I've showed that bottleneck features, which use multilingual non-target languages, can help. So there's a kind of obvious question here: can we combine these two things together? Right. So just as a reminder, the way that the correspondence autoencoder works is we're going to start by having two examples of a word, and we're going to take a single frame of that as input and a single frame of that to use as the target output. Right. So in order to sort of combine our bottleneck feature idea and our CAE idea, it's actually pretty simple, right? These examples in the original correspondence autoencoder, the features in these frames that we're using were MFCC features. But now what we can do is we can just take those words that we've extracted to use as pairs, and we can represent them using our bottleneck features rather than our MFCC features, and just run the correspondence autoencoder as we did before. The other thing that we're going to look at is actually comparing using unsupervised word pairs, using the unsupervised term detection system, versus using gold standard word pairs, right? So that's basically, well, it's supervised, but it's very minimally supervised, right? So it basically says, okay, we've got a handful or more of words that have been identified as belonging, they're the same lexical item. And what you can see from our results is that combining the bottleneck feature idea with the correspondence autoencoder idea does actually help, although with the caveat that in this case it seems to only help when you use gold pairs, right? So our unsupervised pairs don't seem to be good enough to get this to work. Here's our 6 test languages again, and the ones that are working you can see are the bottleneck features in blue, and using the gold pairs of the correspondence autoencoder gives us a higher precision on the word discrimination task. Okay, so that's really nice. I mean, it would have been even nicer if we could have gotten the CAE to work with fully unsupervised pairs. But actually, this idea of using gold standard word pairs as a very kind of minimal type of supervision is really, I think there are cases, and I will show you one in just a second, where actually that's still easier to get than full transcriptions of the speech data that we would normally use to train a supervised speech recognition system. So at this point, I'm going to kind of transition from talking about my own work to talking about some other people's work. Actually, I should also mention that when I'm saying this is my own work, obviously there's other people who've been involved, and one of the people who has really been involved in, I think, all of the work that I've talked about so far is my former PhD student, Hermann Kemper, who also introduced me today, and is from Stellenbosch. And so this next bit of work is actually his work along with several other people from Stellenbosch as well. So I thought it was particularly nice to talk about this, because if it's something that kind of gets you excited, then there's actually people here who will still be here after the summer school to talk to about it. So this is an application of these ideas about improving features to African radio data. So the idea here, the goal, is to try and extend a system for keyword spotting in call-in radio shows that was previously developed to more languages. So my understanding is that this radio system, radio browsing system, is actually currently in use for United Nations development and relief programs in Uganda. But the way that they developed this system was actually using a full ASR, that is automatic speech recognition method, right? So they actually had to use transcribed data. And I'll explain in just a second kind of what the system looks like. But there's, I think, something like, according to Wikipedia, source of all knowledge, there's about 45 different languages spoken in Uganda. Some of these have a lot of speakers, some of them not so many speakers. The idea here is that Uganda doesn't have a strong internet presence, and so actually what people do to try and kind of communicate and understand what's going on around them and what the issues are is they'll call into these radio shows and just talk about issues that are coming up. And so being able to kind kind of figure out what's going on and sort of monitor these radio call-in programs can give us a lot of information about, what issues are coming up and what's affecting people. And of course, those radio programs are, being hosted in lots of different languages. And so I think I'm not actually sure how many languages the system covers at the moment, but they do mention that they were not, it did take quite a bit of effort to develop it for those languages, and they don't have it for all the languages that they would like to. So the idea is, could we come up with ways of trying to make this easier to develop for other languages, not just in Uganda, but perhaps in other parts of Africa or in other parts of the world as well. So let me just kind of run through how the system works and what the idea is of how to kind of get rid of the ASR component. So this is a figure from their paper. And the idea is that you start off with a bunch of audio files, right? So these are the recordings of the radio. And in the version of the system that's currently deployed, you run a speech recognition system over that to give you the results of that, right? So automatic transcriptions. Actually, it's technically not transcriptions, but lattices, if you know what that means. And then once you've got those lattices, you run a keyword spotting system over that. So the idea is basically you have to run full speech recognition on the entire audio sequence and then look for the keywords, right, essentially as text. And then there's several steps after that because there's actually humans involved in the loop and sort of figuring out, okay, once I've got things that potentially have keyword hits, there's people who go in and look at whether they're actually relevant and try and do some additional stuff with it. But the key part that they're trying to improve upon here is, can we get rid of the necessity of having the full speech recognition system? And instead, could we just directly run a keyword spotting system that goes straight from audio to coming back with, saying, oh, here are some files that have this keyword in them. And so the way that works, kind of big picture, is you can imagine what you want to do is you have some examples of keywords, right? So you might have, perhaps people have recorded ahead of time or, on the fly, whatever. Some different people speaking different examples of some keywords that you might be interested in. So things like health or attack or HIV. And then you've got this unlabeled audio collection, and what you want to be able to do is just go into that audio collection and say, okay, do I find any examples of any of these words that match my spoken examples that someone's given me, right? So there's no necessity to transcribe anything at any point. And what you can see is that this is exactly the kind of situation where being able to better discriminate between words and identify, does this bit of speech, is it actually an instance of this word or is it a different word, right? That word discrimination task is very similar to the kind of thing that we need to do here. So hopefully if our features were working better on word discrimination, then plugging them into a system like this should also give better results on this keyword spotting task. And so that's exactly what this paper does. It's not actually working on the Ugandan languages. It's actually doing some experiments, initial experiments. I mean, this actually just came out like 2 months ago, so hopefully they will continue to work on this in other languages as well. But so far, it's been done on this South African broadcast news data, which is in English, but not using any English transcriptions or anything like that, right? So the only label data that's used here is exactly this kind of, individually spoken words as labeled data, right? So they got 24 speakers to come in and record 2 examples of each of 40 keywords, right? So there's really not a lot of labeled data here. But even using just that very small amount of labeled data, what you can see is that including the BNFs and the CAE actually led to very big improvements in this keyword spotting system. So starting off with the traditional MFCC features, there's 2 different measures of accuracy that I'm showing here. So this is a kind of information retrieval task. So one of the measures is area under the curve meaning the ROC curve, right? So Actually, for both of these measures, higher numbers are better. And then the other one is a precision at 10, right? So if we return 10 documents, how many of them are actually, actually have this keyword in them? And so what you can see is basically that, as we move from the MFC-Cs to the correspondence autoencoder, with just that very small amount of training data, we still get a pretty big improvement in the precision and a small improvement in area under the curve. We also get improvements by using bottleneck features, but actually we get a really big improvement showing here for the combining of those two methods. So I think that was really cool, and I was really happy to see people using this for a system that I think should have really nice applications. So what this is showing is that, with no labeled target language data, this idea of using multilingual BNFs can really improve word discrimination a lot, more even than the correspondence autoencoder. It can help with unsupervised segmentation and clustering, as well as with keyword spotting. We did confirm our hypothesis that using more languages seems to be better than just using more data from a single language. And this, well, actually both our results, but also these keyword spotting results seem to show that you can improve the bottleneck features even more by just using a handful of labeled words in the target language. Okay, so that's the summary of this sort of first example of using multilingual data. And my very last thing that I want to talk about is another example of using data from other languages to try and improve the task of interest. So this is now moving to a slightly different area. We're now looking at speech-to-text translation for low-resource languages. So just as a little bit of background, if we're looking at a traditional speech translation system, the way those are typically developed is you would start off by having a speech recognition system that goes from the speech to the text in whatever language it is, and then you would have a separate machine translation system that would take those predicted transcripts and translate them into, in this case, English. Okay, but you can see that that's kind of a problem if you're working in a low-resource language, because you now need actually two different kinds of labeled data. You need both transcribed speech and you need parallel text. So what we're going to try and do here is actually get rid of all this middle stuff and just do end-to-end speech translation. We've got speech in a foreign language, or one foreign language, and translation into another language, which actually happens to be English in this case, unsurprisingly. So we're going to do that. And there's, I think, a few potential uses of this kind of system. One of those is for endangered language documentation. It turns out that there is some documentation of languages where linguists have actually gone in and tried to transcribe the audio very carefully, phonetically and so forth. But that's incredibly time-consuming, and there's not a lot of linguists in the world doing this kind of thing. I think there's already some data where you've got audio in some endangered language and text translation into another language that's typically a majority language in that area. In fact, many people who speak endangered languages may also be bilingual, so they can actually be able to help with this themselves. So that's one area. And I think another potential use case for this would be, as I mentioned earlier, there's a lot of languages that don't even have writing systems. And so instead of worrying about how to write down whatever it is that's being spoken, maybe just write it down in a different language. So the question that we were trying to address here is, what's actually possible with very little parallel data, and can cross-lingual pre-training of the speech component actually help? So the data sets that we're going to use here are, for our parallel data, we had up to 50 hours of Spanish-English parallel data, so Spanish audio and English text. We also had a really, really small data set that's actually from a low-resource language, Mboshi, which is another African language. It's spoken in the Congo. I think it's got about 100,000 native speakers. And that's been translated into French text. And then we also have additional transcribed data from English. We've got 300 hours, and from French, where we have just 20 hours, although potentially you could obviously get more of French if you wanted to. And we're going to use another deep neural network to do this. So I'll try and I'm not going to go through all of the details of this, but I'll try and give you the kind of big picture of how this network works. So here's the architecture that we're using for speech translation. Okay, so the idea of the speech translation system is we get input on, so it's basically an encoder-decoder model. So the encoder is on the left-hand side of this model, and the decoder is on the right-hand side. Right, so our input is going to be, if we're using Spanish-English, our input will be Spanish speech, and we encode that using a bunch of CNNs and LSTM and so forth into some internal representation. And then in the decoder, at training time, we're going to give it the English translations of the Spanish. If you can, I'm not sure how large this is for you to see, but these are actually these are broken up into subword units using a method called byte pair encoding. But basically, at training time, what we're going to get into the decoder is whatever the previous time step correct English word is, we're going to be able to have access to that when we're decoding the next time step. And we have to output our prediction of whatever the next English word or English subword unit is. Okay, so that's at training time. And then at test time, instead of getting the English reference text, we're just going to get the output from the previous step. Okay, so that's our speech translation network. But actually, it's also our ASR network, right? So remember, we're going to do pre-training of this on a speech recognition task. So the only difference there is that our input now, instead of being Spanish speech, is going to be English speech. Right, so the whole idea here is that we're going to use exactly the same network architecture. We're going to pre-train it on English speech to English text, and then we're going to start from that and replace the English speech with Spanish and fine-tune it for the speech translation task. And so the first question that we wanted to ask is, how much data can we actually, get something useful out of, and at the same time, how well does this pre-training work? So this graph is actually showing both of those. Right, so on this axis, we're seeing the number of hours of training data that we used, up to 50 hours. And this is actually showing precision and recall of individual words. Right? So of the words that we're supposed to be translating in this particular sentence, how many of them did we... what's the precision and recall of those individual words? We also computed BLEU score, which, for those of you who know about machine translation, is a much more commonly used metric. And the pattern there is very similar, but it's harder for people to interpret if you're not familiar with MT. So I'm showing here the precision and recall. So what you can see here is that we've got our baseline system that does not use pre-training. That's these dotted lines. And we've got our system that does use pre-training. Those are the solid lines. And pretty clearly, there's a good benefit from using the pre-training for speech recognition. It does seem like that benefit is maybe tailing off a little bit by the time we get up to 50 hours. And you can also see that, when we only have 2 or 5 hours of stuff, we're not, our scores are not great, not that high above the baseline. I should say the baseline basically says just predict the top, I forget how many, the top n most frequent words as your translation. Right? So we're definitely doing a lot better than that. And just to give you kind of some sense of what does this actually mean, here is just a single example of one of the translations. Right? So we've got the Spanish. We actually do have the transcriptions if we want to look at them, although we weren't using them for training. We've got the English translation that was the human translation. And then you can see the different outputs of the 20-hour system, the one with pre-training, the 50-hour system, and the one with pre-training. So you can see that actually, at least for this example and for a number of examples, it's actually doing reasonably well. I mean, they're not fantastic, perfect translations, but they're actually surprisingly okay. So it seems like we can do pretty well with not that much data. And the other thing that we looked at is which of the parameters in the when we're transferring our pre-training parameters, which parameters are actually the most helpful. So there's a lot of stuff showing on this, but basically the bottom line of this figure is that it's actually the encoder parameters that really are helping us, right? So the encoder is the part that's going from the speech to internal representation. So that's kind of interesting because actually our speech recognition system is going from English speech to English text, and our translation system is going from Spanish speech to English text. So in some say, you might kind of think that the decoder, where we just decode internal representations to English, which is actually the same, or should be the same in both cases, that would help the most. But interestingly, that's not the case, right? It's the encoder, which kind of, gives us yet more evidence that, the actually encoding speech and figuring out what the right features are and abstracting away from stuff that doesn't matter, like that's a really hard problem when you have low resource setting, right? So even, learning that on a completely different language is actually helping us a lot. And then finally, we sort of looked at what would happen if we tried the Embauchy French data. We weren't actually hugely optimistic about this because our Spanish-English results kind of suggested that below 5 hours, like we're not going to get very good results anyway. And we only have 4 hours of data, but we did the experiment. And I mean, again, the results are not great, but I think the nice thing is that they do at least sort of qualitatively show the same pattern. And in fact, what we found was that the best results that we were able to get here was by pre-training 2 different models. We pre-trained an English ASR system, we pre-trained a French ASR system, and then we took the encoder from English, which was better because we have more English speech data, and we took the decoder from French because this Embauchy French model needs to go into French, so maybe we learned something about French there, and we combined the 2 of those. Right? So that is clearly working a lot better than the model with no pre-training. I would assume that if we had more than 4 hours of data, this, all of these numbers would go up a lot. And it's also doing better than this baseline, which is just predict the top 8 French words, although clearly not a huge amount better, right? So this is clearly, 4 hours of data is pretty much pushing the boundaries. Okay, so to summarize that final part of the talk, right, we certainly are able to get pretty okay translations with just 20 to 50 hours of parallel data, which is kind of nice. It sort of, gives you a sense of what is possible. And also that if you're doing that kind of thing, that pre-training to help on the speech side seems to be really important with this kind of data. But I think there's also a lot of nice ideas here for current work that we're already doing, and as well as future work. So at the moment, my student Samir Bansal, who is doing this work, is also looking at whether these quality of translations is good enough to maybe do something like a cross-lingual version of the keyword spotting task that I talked about, or maybe some kind of topic modeling or other sort of document clustering in the target low-resource language. And then another obvious question, given that the previous part was about multilingual training and we only used one language for pre-training here, could we actually improve things further by doing multilingual pre-training? So, just to wrap everything up, what I've tried to convince you of here is that low-resource speech technology is really important for universal access and language documentation, and that speech is really a very difficult kind of data to work with, and pure bottom-up learning systems are just not going to work very well. So we really need to be thinking about other sources of information that we can use. And so in the first part, I talked about using monolingual information, top-down information to improve the features, and joint learning for the segmentation and clustering task, and then using information from other languages in the second part of the talk, where we can either use multilingual bottleneck features or pre-training. But hopefully, this is a pretty big space, and there's not, there's a few people working in it, but I think there's a lot of room here for other researchers to come in and come up with both novel methods, machine learning methods, but also, certainly there's lots of other applications and, more different languages to work on and lots of other exciting stuff. So hopefully some of you will be interested in doing that. And finally, I just want to thank everybody here, the organizers of the Machine Learning Summer School, my co-authors on the work that I talked about here, and also the people who developed this further and that really cool keyword spotting paper. So thanks to all of you, and I will be happy to take questions.